Okay, today we're going to be looking at Archimedes' principle, or buoyancy. And I'm going to start this off with a little diagram here. The diagram is going to be of a fluid. Let's say this is a container of some sort of a fluid. It's all filled. And there's an object in here, and I'm going to make the object a little cylinder here. Now, on this object there's going to be a force pushing down and a force pushing up. The force pushing up is going to be P2, the pressure there, times the area. The force pushing down is going to be P1 times the area. There's going to be a difference between these forces, as we saw last time, due to the height of this cylinder. And so we're going to call the buoyant force the differences between these two forces. And it turns out it's going to be P2A minus P1A. I'm going to rewrite this as P2 minus P1 times A. We saw last time that P2 minus P1 times A is actually rho GH, rho being the density of the fluid. And so I ultimately get here that FB is going to be equal to rho GH times A. And if I rearrange this, I actually end up getting rho HA times G. The reason I did that is because H times A is volume, and volume times density is mass. And so this whole thing is mass, which means this all equals M times G. This is a useful result in that the buoyant force on any object is equal to the weight of the fluid displaced. It's the weight of the fluid displaced. And sometimes we write that just and say, force of buoyancy is equal to the force of gravity of the fluid displaced. Now that has some important ramifications. We can look at that with an example. Here's a typical example. Suppose that we want to look at a raft. I'm just going to take an example here and to say, well, here's a raft. A little wooden raft is sitting here floating in the river or lake, and it's there. It's just floating along here. We're going to say that this raft has a height of 0.3 meters. It has a width of 4 meters and a length of 4 meters as well. So it's 4 meter by 4 meter by 0.3. The volume of this raft would equal 4 by 4 by 0.3, which ends up being 4.8 meters cubed. We're going to say also that the density of this raft, rho of this raft, is going to equal 550 kilograms per meters cubed. The question here that I want to ask is, if it floats, how much of the raft is beneath the water? So how much of that raft is actually floating beneath the water? Let's take a look. First thing we can figure out is we can find out the weight of the raft. I'm just going to call that the force of gravity of the raft. And the weight of this raft is going to be equal to rho times V times G. The reason being is, again, this is mass. Density times volume will give me the mass, and that's all I know for this. And so I can plug in those numbers, and you ultimately get here 26,000 newtons. Now, if all of this raft were underneath the water, the buoyant force, and I'm going to call it the maximum buoyant force, the maximum buoyant force here is going to equal the weight of the fluid displaced. And so the weight of the fluid displaced will be the density of water times the volume of whatever is displacing it. In this case, it's the raft. So I'm going to say the volume of the raft times G. Well, if we plug in our numbers here, you're going to get 1,000 times 4.8 times 9.8, which gives approximately 47,000 newtons. The reason I'm showing you this result is that if the entire raft were underwater, this is how much buoyant force would be pushing on it. We know this thing is in equilibrium, and we only need 26,000. So first of all, this shows us that it does float, and that not all of it will be beneath the surface, because of it only needs to combat or fight 26,000 newtons. So what exactly is the buoyant force then? Well, if we look at our raft here, okay, and we take a look, we're really interested in the 0.3 is going to change. What I mean by that is the buoyant force, we want to match that 26,000 newtons. Now the 26,000 newtons, well, is going to be the weight of the fluid displaced, which again is the density of water times the volume of the raft that's submerged. I'm going to call it V sub times G. This will be the mass of water displaced times gravity, which is the weight of the fluid displaced. And so if I put in my numbers, you're going to get here 1,000 times the volume that's underneath, which will be 4 by 4 by some variable h. We don't know what that is. It's no longer 0.3 anymore, times 9.8. Now if I do this, I'm going to get a height of approximately equal to, it's around 17 meters. It's around 17 meters. Oh, pardon me, 0.17 meters. 0.17 meters, which means a little over half of it will be underneath the water. There are faster ways of solving this problem, though. Because I'm looking at, the force of buoyancy, which equals the rho of the fluid, the density of the fluid, times the volume that's actually underwater, times g. Because of this, I want to know, when does this match the object's weight? When does that match the object's weight? And if we recall, the density, or the weight of an object, is just the density of an object times the entire volume of that object times gravity. This will be mass times gravity. So when are these two equal to each other? Well, if we do some quick substitutions, I see here that g can cancel out. And what I get is I get a ratio of the density of the object over the density of the fluid that it's in, if that's equal to the volume that's underneath, the volume that's submerged, divided by the volume of the object. This could easily solve our last question. And in that last one, we could have easily taken the ratio of these densities with the volume of the object to find this 0.17. It's a nice handy way of doing this, these problems involving buoyancy.